power series is defined to be a series from k equals 0 to infinity, although you could start at 1 or 2 or whatever is appropriate for the series, whose rule is generated by some constant times x minus a to the k power. And notice that as we move from k equals 0 to infinity, we end up with something of this form. The constant you get when k is 0 plus the constant you get when k is 1 times x minus a plus the constant you get when k is 2 times x minus a squared. And this just keeps going. And our nth term is the constant you get for the nth term times x minus a to the n power. And notice the next term after the nth term would be the n plus 1 term, and after that you would have the n plus 2 term, and so on and so forth. Now this particular power series is said to be centered at the value of a. Basically what that means is that our series can match up with another function, potentially, and it begins to match up at a specific x value, in this case a, and may continue to match up in either direction from a. It might look something like this. From a, our series and our function can match up in this direction and in this direction for a while. Right, and after a little bit, the graphs may diverge. So even graphically, it might look something like this, where you have, say, the graph of some function, and I'm just making this up. This isn't coming from anywhere. Right, so that's some function. And we could have a series that matches up like that. And a would be maybe here. And notice how they match up in both directions. Roughly, it should be the same distance, right? Where this distance, I'll say from B to C, where graphically the things match up, you can think of as the interval of convergence. And the distance from A to B or A to C would be the radius of convergence. Now the simplest of all power series is centered at 0. And that would be the power series from k equals 0 to infinity of x to the k power, and that's equal to 1 plus x squared, and then eventually you get to the nth term, and after that you have the n plus 1 term, so on and so forth. Now this is a geometric series whose starting value is 1 and whose common ratio is x. And you should recall that since this is a geometric series, whenever the absolute value of x is less than 1, this series converges whenever the absolute value of x is greater than or equal to 1, the series diverges. But not all power series are easy to identify, right, or things that we would know offhand necessarily. And so we use the ratio test to identify when series converge. We'll use the ratio test a lot. So imagine we had the series from k equals 0 to infinity. We'll complicate this a little bit. This happens to be the series x to the k power over 2 to the k power times k plus 1 squared. Now you might be thinking to yourself, well, how is this a power series? And it's a power series because the constant in this case is 1 over 2 to the k times k plus 1 squared, right, times x to the k power. Maybe we could look at this as a geometric series, but it's already complicated a bit. So we'll use the ratio test instead. And recall that the ratio test wants us to consider the limit as n goes to infinity of the n plus 1 term. So in this case, we will have x to the n plus 1 over 2 to the n plus 1 times n plus 2 squared. Right, we want the absolute value of this. And it's divided by the nth term. And if I'm going to divide by the nth term, that's the same as multiplying by the reciprocal. So the reciprocal of this would be 2 to the n times n plus 1 squared over x to the n. And to simplify this down, we would have to be very comfortable with our exponent rules. So by the ratio test, I'll start with the x terms. X to the n plus 1 is the same as x to the n times x. 2 to the n plus 1 is the same as 2 to the n times 2. Can't really break down n plus 2 squared, but I should recognize that if I multiply that out, it would be a second degree polynomial. And I'll have 2 to the n and n plus 1 this squared and x to the n. And just by having some knowledge of my exponent rules, a lot of things are going to divide out now. So I'm still looking at the limit as n goes to infinity. The x to the n's divide out, and I'm left with just x. The 2 to the n's divide out, and I'm left with just 2. And I have n plus 1 squared in the numerator and n plus 2 squared in the denominator. Now this is going to be a second degree polynomial, which means that the limit as n goes to infinity of the entire thing will end up being simply the absolute value of 1/2 x, right, or just x over 2 if you prefer. Well, how does that help? Well, we've narrowed this down, and we know that when this is less than 1, then this will converge. And this means that any time x is between -2 and 2, this will converge. Now the problem with the ratio test is we aren't sure what's happening at the endpoints. We will have to test -2 and 2 independently to find out what's happening at the endpoints. If we were to consider when x equals 2, well, when x equals 2, that means that our series from k equals zero to infinity will be equal to 2 to the k over 2 to the k times k plus 1 squared. Or if we simplify that a little bit, we'll have the series one over k plus 1 squared. And this is a series that we can evaluate by direct comparison with the series k equals 1 to infinity of 1 over k squared. And I know that this converges, so I know that this must converge. And someone may ask, well, you didn't use k equals, the original series was k equals 0. How does that change things? Well, we can consider that we're just going to think of this series from k equals 1 to infinity to compare them directly, and that one extra term will not affect things in terms of convergence, right? That very first term being 1. But by direct comparison, we know the two series converges, which means if we go back to our interval, we know that x can equal 2 and it's still going to converge. Now we have to do the same thing with x equals -2. And when we substitute -2 in, we end up with the series, and we'll go from k equals 1 to infinity again, which is -1 to the k power over k plus 1 squared. This is an alternating series. And by the alternating series test, this will converge, which means we can finally conclude that our interval of convergence is from -2 to +2 inclusive, or we can say the radius of convergence is 2.